I guess now the constructive part of my talk starts. Matt alluded to these constructions and Rongchan alluded to them. And so now we should get our hands a bit dirty. That you want to construct weak solutions of the Euler equation. So how would you construct solutions to any PDE? Like, it's a question. Like, there is one good answer.
Approximate solutions.
Approximate solutions and Newton iterations, right? That's the best in the business. You can't do better than that, right? So you guess something and then you Newton iterate and you do something, right? So let's try. Okay, so you guess something, you have a guess V. Because you are not the Almighty, you didn't actually guess an exact solution, right? You've made some error. You plug this in and you just compute your error. Some pressure, remember the pressure is always computed in the same way. And the error, because it has zero mean, you're going to write it as divergence of some. Of course, you were smart enough to pick an incompressible vector field. So let's say you didn't make an error there. Okay, so now what would Newton iteration say? It would say that, let's say this is maybe V0. Newton iteration would say that you should construct the next iterate such that V1 is V0. The functional derivative of the Euler equation evaluated at V0 inverse. So let's write D of Euler evaluated at V0 applied to Euler evaluated at V0. Of course, Euler evaluated at V0. Okay, so what's the linearization around V0 of Euler? It's dt plus V0 dot grad plus gradient V0 transpose dot grad. This is the linearization of Euler around V0 inverse. And Euler evaluated at V0 by definition is a divergence of R naught. So this would be the best in business way of iterating, and you keep going, right? This is the Newton iteration. There is nothing better than the Newton iteration. Then this, of course, works, but this is only going to work if you are in a setting. The Newton iteration fundamentally is a linear method, right? It's treating the nonlinearity as an error, and it keeps on pushing the nonlinear effects into higher and higher, basically to infinity. So this is gonna work if you are in a functional setting in which the linear term dominates the nonlinear term. In terms of dissipative PDEs, where we have a natural one-parameter scaling of the PDEs, that would be called subcritical or critical spaces. And when you have this one-parameter scaling group, if you are in a supercritical setting, this is gonna bomb. It's not going to work. Of course, Euler has a two-parameter scaling semigroup. It's not just one parameter. So it's not even clear what I mean by supercritical and subcritical, because I do have a two-parameter scaling semigroup. But of course, I could basically tell myself that my scaling respects continuous in time with values in L2. It wants to respect that. That imposes already a restriction on one of the scaling parameters. And this problem is supercritical. Okay, so this is just not going to work because nonlinearity dominates. I guess second attempt. You always start from a guess, right? Because you need to start somewhere. So the next thing is maybe, okay, so maybe to do compute a V1 in a smart way by adding to your guess a perturbation W, which is incompressible, hoping maybe that whatever you've added, this new guess is better than your old guess. What would this mean? It means that if you write dt V1 plus the divergence of V1 tensor V1 plus the gradient of P1, you've made a new error. Hope is, of course, that the error you've made now is smaller than the error you've made before. In some norm, be a natural thing. So imagine now, what would this perturbation possibly depend on? What could scripty W possibly depend on? Well, I mean, it's going to depend on V naught and R naught. It can't really depend on much else. In fact, experience with linearized Euler should tell you that it doesn't actually depend on V naught, but on the gradient of V naught, because transport equations really care about the gradient of the vector field in order to solve them, right? You care about Lipschitz timescales. You don't really care about the vector field itself. And this guy already has the gradient. So it's automatically going to have to depend on your old thing and on the gradient of V naught. Hey, I mean, this is not saying much. So you need to inject something, right? And maybe what you're going to do is you're going to say that if your original guess maybe had a smallest scale present in it, that the new thing you're adding is at the higher, even smaller scale, so a higher frequency. The thing you're adding does not depend on X, because I was about to write X and T, by the way. Maybe it doesn't depend on X and T, but at some very high frequency version of X, capital lambda, high frequency, so I should write it backwards. Capital lambda is large. Maybe it depends also on some fast time variable. Oh, what letter? Can you please give me a capital Greek letter? I can't think of a single, oh, gamma, okay, whatever. Where lambda and gamma are large. And what I mean by large is really, lambda should be much larger than any oscillation that I see in here. And capital gamma should be much, much larger than any oscillation I see in there. So if you really take this perspective, and this is really like a fast variable, of course, there's xt dependence there, but it's slow. And maybe this is a master function. So this would be the perspective you would take if you were trying to reduce the problem to a cell problem in homogenization, if I would also maybe tell you that I want periodicity in Y and S. My first attempt would be to do this. So to reduce it to a problem in which my goal has now become, my goal is always to make R1 much smaller, right? So the goal is to minimize what? Some norm, I don't know what norm, of R1. Who is R1? Okay, maybe I do need to write one more thing before I write this. Okay. You have an equation for V1 and you have an equation for V0, so subtract them. You're getting the divergence of R1 plus some pressure gradient, T of little w plus V naught gradient little w plus little w dot grad V naught. So this is the linear part, and then you have the nonlinear part. And then you have your old air. So maybe your goal, so you see that R1 is now actually really a function of your old friends and of your new friend. So maybe the goal is to minimize some norm, which I do not know what it is, of inverse divergence of this whole thing in some norm. Minimize it how? Well, maybe under this ansatz. Okay? So you have maybe this ansatz. And of course, if you state it like this, you have to be a bit more quantitative. What's your norm? What were the norms of these objects? So under this ansatz and some bounds, budgets. We can't just print money like the Fed. We have a budget. Right? So this would be a perspective that you could employ. And of course, you could plug in this basically corrector ansatz into the equation, plug in that scripty W in there. Assume that these gradients only act on the fast variables, right? This is how you deduce your cell problem. So this would be a ds of W plus V naught dot gradient of little y. Of course, if I take a ds, I need to put a gamma or a 1 over gamma. There's a lambda in front here of little w plus w dot gradient naught plus divergence of capital lambda w tensor w plus r naught. And now you can try to design capital W really as a function of this minimization problem as stated like this doesn't really make any sense because I didn't put any constraints, I didn't put any norms. But there is a way, and you will see that I could actually put constraints and some norms, and maybe I should just speak for myself, but I have no idea how to minimize this. I don't even know how to prove there's a minimizer or anything like that. Okay, I have no clue. So instead of actually computing this in the good old-fashioned way, which would be this one, what we're going to do is we're going to make this as a, we're going to use this to be some kind of guiding principle rather than a literal, we're not going to literally solve a cell problem, but we're going to use it as a guiding principle for us to really design the perturbation. And we hope that if we're good enough, maybe we're not achieving the minimum, but maybe it's good enough. I just want to tell you that this perturbation which we're going to design is not coming out of the blue. There is something behind it, but you should really view this something behind really more like an intuition rather than the literal minimization problem or the literal cell problem. So now let's actually, so I just wanted to say this as an intuition. And by the way, this intuition already tells you something. So what does it actually tell you? Remember that this function bold W, capital W, has a fast dependence with respect to space, right? If you look at all these terms, let's use this notion that if you have an object which is fast multiplied by an object which is slow, of course it's going to modulate the fast object, but it's still a fast object. You know, sine x times sine 10x is, you know, kind of like sine 10x, right? It's 9 and 11. Okay, so this is fast. This is slow times fast, it's fast. This is fast times slow, it's slow. This is slow. So far, this is the only slow object. And this is fast times fast. So these terms, which is what the Nash scheme was trying to do by saying that I'm going to invert the linear part onto the error, they're not going to help you. They're fast. And you're trying to cancel something which is slow. It's just not going to work. So you better use the fact that the product of two fast functions has a contribution which is slow and the contribution which is fast. Sine squared of nx has a 1/2 piece, and it has a 1/2 cosine 2nx, right? So that's what we mean here. So you already know somehow that the dependence on R0 on your master function has to be in such a way that the L2 or whatever, the average in the spatial variable, and what is the average but the integral, right? So you already know that the integral over the box of your master function in 4 variables, 1, 2, 3, 4, and you're averaging, and let's call this the second entry R, sorry, the first entry R. This is the slow part of that thing. This better equal somehow minus R0. Because otherwise, there's just no way. If you're doing that, let's see what else this quote-unquote cell problem teaches us. Okay, so this would be one constraint that we're going to have to satisfy somehow. Another constraint that we're probably going to have to satisfy is the following. The high frequency parts, the fast parts of this, and this are now errors. If capital lambda is huge and capital gamma is huge, those errors are going to have to go into the new stress. Now, let's take a breather. We do have an inverse divergence there. The inverse divergence, okay, first of all, divergence as an operator has a huge kernel. Inverse divergence, we should talk about that. Okay, we'll talk about that. But essentially, if you apply a -1 order operator, like inverse divergence would be, applied to a fast object, it should gain you 1 over that frequency, right? So when we apply inverse divergence, in some sense, we're going to gain a capital lambda here. We're going to gain a capital lambda here. We're going to gain a capital lambda there. And we're going to gain a capital lambda there. So in some sense, you already kind of know that it's not hopeless, okay? But let's stare at this just for a bit longer. this term, hoping that you're going to make it small, maybe combined with these other ones. So the only way that you can do that is that with respect to this quote unquote fast variable, this master function essentially solves the equation divergence of W tensor W plus some pressure gradient is 0. And also maybe this transport plus stretching is 0. I wrote them separately because they're really of a separate nature. So the idea that I'm going to try to make this as close to 0 as possible is the idea that with respect to this fast variable, my master function should be a stationary solution of Euler. Divergence of this tensor this equals a pressure gradient is the stationary Euler. It's the definition of stationary Euler. So I should know that at least to leading order, my master function should be a stationary solution of Euler. Now to next order, I also kind of know that my master function should somehow be adapted to the flow of dt plus v naught dot gradient. It should be adapted to this flow because I do see the transport operator there. So I know that my master function is going to have to somehow incorporate the Lagrangian coordinates associated of that flow, the characteristics of that flow. If I'm not going to respect the characteristics of this flow, I'm going to be in trouble. And then there's this term, and this is the one that I'm going to try to estimate today for you. But I just meant to have this slide here, and it's on purpose a bit all over the place. It's just to see what is the basic intuition we can gain from basic considerations, okay? And now we're actually going to write things down.
Vlad, how far can you get if you don't adapt the master function to the transport structure?
If you don't adapt it at all, like really at all, I don't even know if you can get C0. If you adapt it in the most silly possible way, where you just say constant plus CT, when that constant is the mean of V naught. It's not really V naught, but it's the mean of it. If you're just ruling out the mean, you can already get some Hölder exponent, a marginal Hölder exponent. So let's put some quantifiers on this idea. Okay, so we're going to design a so-called Nash iteration, which should not be confused with Nash-Moser iteration, which is Newton plus modification. Okay, that's not the same. Just Nash had many good ideas, let's say. So we're going to have a sequence of approximate solutions indexed by a natural number q, and a sequence of errors RQ stands for Reynolds stress, because when you do, let's say, direct numerical simulations of fluids, you only have access to so many Fourier modes on your computer. So in some sense, you have to project away the super high frequencies. And if you do this projection properly, there's an error you make, which is called the Reynolds stress. And people who do simulations, they model this Reynolds stress. This is called Eddy Diffusivity. And if you hear words like this, it's a specific model for what the Reynolds stress is going to be. We're not going to do that, okay? So we're going to have a sequence of objects like this. They're going to solve the following PDE and have Euler plus error. By the way, it's nice, it's not necessary, but it's nice to notice that the trace part of this times the identity is a gradient, right? The divergence times the identity is a gradient. So I can actually take the trace part and hide it in the pressure, and I will not have done anything. So from now on, I'm going to put a little circle on top just to emphasize that it's traceless, because I've hidden the trace in the pressure, okay? So I don't know, these objects are going to satisfy this thing, and they're going to obey certain estimates, okay? So now in order to specify estimates, I need parameters. And I'm going to have two types of parameters only, well, three. I'm going to have a frequency parameter. And by frequency, I really mean Fourier frequency in space. This parameter is lambda sub q. Matt alluded to this earlier today, that ideally lambda sub q would be 2 to the q or something. It's not going to be that. It's going to be super exponential, a to the b to the q, where a is huge, but b is going to be as close to 1 as I can. So, which is to say that I'm going to try to make it as close to geometric as possible without breaking the proof. So I'm going to try to make b minus 1 really small, but b more than 1, always. Okay. So b is 1 and a bit. And ideally, it will be as close to 1 as possible. This is the frequency parameter. Then I'm going to have an amplitude parameter, and it's convenient to, okay, so I'm going to call this delta sub q. And for reasons that are going to appear later, I'm going to relate the amplitude to the frequency by a power law. Okay. A priori, you could leave them like this, make them completely unrelated. But again, due to experience of Camilo and Laszlo, it's actually convenient to relate them. And it's going to be minus 2 beta. Okay. Beta is a positive number. Frequencies grow super exponentially. The amplitudes decay super exponentially. And then we're going to have a time frequency. Okay. Because everything depends on time. This is a space frequency, and now I want the time, a temporal. Why do I need a temporal scale in the first place? Remember how I told you that we're going to have to satisfy, at least to leading order, the characteristics of this flow. Characteristics of flows are only traceable for an amount of time which is inversely proportional to the Lipschitz norm of that flow. Afterwards, you're not good. And for those of you who know numerics, this is called the CFL. We're going to need a temporal time scale, and keep somehow in the back of your mind that it's going to be related to an inverse time scale, inverse Lipschitz scale, quote unquote. Okay. It's not exactly, that's why I keep on using. Anyway, this is going to be called tau sub q. I do have an amplitude and a frequency. For later reasons, you will see why I can actually relate them. This is not an independent parameter. So please allow me to write this, and I'll tell you later why. So it's going to be this. And just as a sanity check, if this has units of frequency, meaning 1 over length scale, and this actually has units of amplitude, which are units of velocity. Velocity is length over time. So this is 1 over length times length over time gives you 1 over time, and time inverse is a time scale. Okay, so just for sanity reasons, this has the right units. I have these parameters. Now with these parameters, I'm going to impose that throughout my iteration, certain bounds are satisfied. The minimal thing I want is that as q goes to infinity, so q is a natural number. As q goes to infinity, I'm going to want this error to go to 0, right? And somehow you will see why. I mean, I can explain it already. I should explain it already. Remember, our goal is to construct H1 solutions. Half is an L2 based Sobolev space. We have two L2 type functions. Their product is an L1 type function. And we just said that we're in a regime where the nonlinearity is going to match the stress. So if this is an L1 type function, this has to be an L1 type function. I'm going to assume throughout my iteration that this in L1 is less than an amplitude, but for reasons that are maybe not so clear now, it's good to put q plus 1. I'll explain why in a second, of course. So I'm going to assume this throughout my iteration, and if I succeed, this has the property that my stress in L1 will converge super geometrically to 0. So in particular, if I manage to prove that my V's also converge, in the limit automatically I get a weak solution of order. Next thing that I'm going to say is that remember that we also want not just H1 solutions. Maybe I'll do that later. Yeah, anyway. So the next thing I'm going to do is I just said it. I would like my VQs to converge to something, right? So of course the VQ, VQ is my original guess plus the summation over Q prime less than Q of VQ prime minus VQ prime minus 1. So this is my original guess that Scott made me do. So now this one is going to converge to something if this series is summable. I'm going to write here is not something about VQ, but about the so-called increments So this I'm going to denote by WQ prime. So WQ prime in general will be VQ minus VQ minus 1. Okay. So here, instead of saying something about VQ, I'm going to write something about WQ. And through this, you can always deduce one from the other. So what I'm going to say is that WQ plus 1 in L2, we kept on saying this many times now, the stress is quadratic in velocity. So this has to be delta Q plus 1 to the 1/2. Now, you can do this plus the intuition that this has this frequency. And the reason I wrote Q plus 1 here is that this has the next frequency, right? Keep in mind, we keep on adding higher frequency objects. So if this has frequency lambda Q and this has frequency lambda Q plus 1, and it obeys these bounds along with their derivatives, you can actually close this scheme. You only get an H1/2 solution. In addition, we want the bounded solution so that we can do H1/2 intersect L infinity, which contains the correct constant in E and TT space. So in addition to this, we're going to want L infinity bounds. What if I do this 1 here? Then this should be square root of this, and that also 1. If these are all order 1, this series is not summable. But keep in mind, I never said that my solutions are actually in L infinity. I always wrote L infinity minus to mean that it's in any LP space except not L infinity. Okay, so this is so far consistent with everything. As I said, I'm not telling you entirely the truth because otherwise we would not be able to finish this in 3 lectures. What I should really write is not just intuitively this has frequency lambda Q and intuitively this has frequency lambda Q plus 1. I should encode that in an estimate. The correct way to encode that would be to say, if I take a gradient of RQ in L1, I get the same size, maybe it's n dependent. For every single gradient, I pay frequency or 1 over length scale. It's really what it means for me that this lives at frequency lambda Q. That when you act with a gradient on it, you pay what the inverse length scale costs. I also said that we're going to have to somehow respect the flow. So I need one more piece of notation to do with the material derivative. We always need to respect not the time derivative in the Lagrangian coordinates of the previous approximation, which are the material derivatives. So we need to respect this derivative. I don't always write this. I'm going to use an old notation, dt sub q. So whenever you see capital DT sub q, it really means this material derivative. And respecting material derivatives means that if I take dt sub q to any other power m, I should also know exactly what that costs. Every material derivative should cost me an inverse timescale. So it should cost me, and the same for the increments. So it has the same amplitude technically, but I need to pay costs. This is at a higher frequency. It's q plus 1 with respect to space. So it's lambda q plus 1 to the n. But the material derivative is still the old material derivative, so it's still tau q inverse. At any time, feel free to correct me if I'm going to make mistakes, because I'm going to make mistakes. Of course, in L infinity, you want the same thing, but this becomes 1. If I write L infinity there, I also want to say that it's the same thing, but with a 1. Okay, so 1 for L infinity, 1. Any questions in terms of simply what are the things I'm going to propagate through my induction? So on the board now you have what equation VQ and RQ satisfies, what bounds they're going to satisfy inductively. And I hope that I will be able to indefinitely produce a next step in the induction with these 4 properties. I mean, it's not 4, these 2 imply the other, right? So this implies, of course, this by sending n and m to 0, and this implies this by sending n and m.
Vlad, I have a question.
Yes.
This is Hiro. Sorry, I'm
Hi, Hiro.
watching for the hotel room. But anyway, so here you put the strong norm and weak norm. Like strong norm is L infinity and weak norm is L1 on the remainder and L2.
Yep.
And I remember like 10 years ago, like Camilo's talk or whatever, the strong norm is maybe C and the weak norm is C minus 1 or I don't know. But then here you use the strong and weak norms from in the Lebesgue spaces, right?
Yeah, because if you want to capture intermittency,
yeah, okay.
If you want to capture intermittency, you simply cannot work in L infinity-based spaces. We discussed, so if you want to go with regularity above 1/3, which is our goal. So remember, our goal is to get regularity in H1/2 intersect L infinity. If I want to go above 1/3, and a half is really above 1/3, I really have to give up on L infinity altogether. So I have to go to L2.
And which is the first work which left this regime of L infinity-based space using the strong weak norms?
Work is, I think, my paper with Tristan on Navier-Stokes.
All right, thank you.
That's the first one. Thank you, Hiro. And please do interrupt me. I feel like if nobody interrupts me, I'm just talking to myself.
And so why is it that the material derivative only picks up the what's it called, the temporal scale, and not like because there's a space derivative too? Is it just because you're only going in a short time?
So it turns out that if you look at the time derivative separately, or at this derivative separately, they each cost a lot. They each cost lambda q plus one, lambda q. But the combination of this specific material derivative costs less. And you notice that this is much less than lambda q inverse by this much. And so it's somehow, you could choose not to do this, right? Nobody says you have to do this. You could try not to do this. The outcome will be that you'll get less regularity. So it turns out that if you really want to milk as much regularity as you can, you really have to respect the dynamics, the linearized dynamics, at the same time that you respect the nonlinear term. And if you could choose not to do that, you could choose not to propagate any information on these. But then that's going to bite you back, and you're going to close the scheme, but you're going to get less regularity. And at this point, it's not even clear, I think, to most people who regularity even is. You have so many parameters. I do want to address this. Does that sort of answer?
Yeah.
Okay.
Hey, Vlad, can I ask just to follow up on that? Is this just because you need the high frequencies to ride on top of the low frequencies? Like the fluid is pushing itself around, right? So the high frequencies have to, if you try to fight that, then you'll get garbage or something.
Absolutely, Scott. The high frequencies, they're just carried around by the mean flow, and the mean flow is just the slower part of the fluid. It's like in geometric optics, the fast wavelet is being transported around by the sloshy slow flow. And that's what we're trying to put.
This is a very, very basic question, but you said that you want to take B very close to 1 so that it's almost geometric. So when B is equal to 1, I don't understand how, you're not getting a geometric scale.
Yeah, of course, because the limit of 1 plus epsilon to the n as epsilon goes to 0.
Oh, I see. Okay.
Yeah, but we'll talk about this. Like, it's not even clear now why I want B close to 1, right? I just wrote parameters on the board. It's not even clear.
I'm just trying to understand. You said some intuition about it being close to geometric. I see what you.
I hope to address this specific question. Okay, so for the moment, and by the way, there's two things that nobody asked me, because math is way too polite to interrupt me. These are functions of time and space, right? But I wrote L1 and L2, and I didn't specify what in time and what in space. All the norms I'm writing are in space. With respect to time, it's always C0. And this is why I'm never going to write it. In time, it's C0, always. Okay? So these are always sub X. All these norms that I'm ever going to write down today and tomorrow. And in time, it's C0. Second thing, for which n and m do you need to do this? Do you need to propagate 1 derivative? Do you need to propagate 10? And turns out you need to propagate essentially infinitely many. Infinitely many, it would be if they would be geometric. If B were 1, you would need to propagate infinitely many. But because B is not exactly 1, you have super geometric. At some point, this is overtaking somebody. As B goes to 1, the number of M and N I need goes to infinity. So let's assume for some reason that this iteration works. What does that give you? Let's just, before we try to close the iteration, let's see what it buys us, because otherwise, why would we close it? Number one, do these bounds imply that my VQ converges to somebody? And the answer is yes. Let's write this again. So let's see in what norm this is summable. Okay, that's the first step. In what norm is this summable? We already decided that in L infinity, it's not quite summable, but it's almost. Right? How about in L2? Or how about in HS? Compute the HS norm. My first guess is smooth because, you know, I'm not going to be crazy enough to not pick a smooth initial guess. How big is that? Well, I don't have HS information, but I have L2 information and L2 information for the derivative. So by interpolation, I have HS information, okay? So by interpolation, this guy is less than WQ prime in L2 to a power, and the gradient is to another power. Power is S and 1 minus S, right? Up to a constant, which depends on S. This guy, I said it's less than delta Q prime plus 1 to 1 minus S. This one is going to be a gradient. What does the gradient cost? A lambda. And then we have the amplitude. I'm an idiot. This is divided by 2. It's 1 over S, but there's a 1/2 here. I forgot to write the 1/2. By the way, stare at this and at this. You will notice they're the same up to an inverse, right? I'm telling you that tau Q inverse is 1 over the Lipschitz timescale. Now I'm telling you that it's actually 1 over the H1. This is a peculiar feature of these LP-based Nash schemes. You don't have access to L infinity. You simply don't. You do not have access to the Lipschitz norm. You have access to the H1 norm. So of course, what you should do, how do you can't solve ODEs on a timescale which is 1 over the H1 norm? You just can't. So what do? Well, if I have an H1 function, I can chop it off into level sets. Chebyshev is going to tell me how big each level set is. But on each level set, I will have a Lipschitz bound. And so essentially what we're going to have to do is we're going to have to chop up these functions into level sets. And on each level set, we're going to have to do a slightly different analysis. So this 1 over the H1 norm is in essence acting like 1 over the Lipschitz norm, modulo the fact that I'm not telling you yet what to do with level sets. But we're going to have to do something with level sets. Okay, so just keep that in mind. Okay, so let's compute this out. Okay, so the S over 2 cancels the S over 2. Delta Q plus 1 to the 1/2. But who is delta? It's that, right? So when I do 1/2, I just get minus beta and plus S. Is this summable? Given that lambda blows up super geometrically, this is summable if S is less than beta. If S is any number less than beta, then VQ converges to some V in HS. Of course, C0 in time, always. So this number beta, given that it's really arbitrarily less, the fact that the regularity can be arbitrarily less than beta should really mean that beta measures the regularity of my solution. So we've identified one of the meanings of these parameters, namely of this one. Parameter measures regularity of the limiting solution up to any epsilon loss, which we're never going to talk about. We've elucidated one thing. So if we are able to do this, not only do we get a solution, but we get an H beta quote unquote solution. We're also going to be almost in L infinity. How about the Reynolds stress? Well, the Reynolds stress goes to 0 in L1. By the definition of weak formulation, in the limit, this V is going to be a weak solution for it in H beta. So if we succeed with this iteration, in the limit, we will A, construct the weak solution of Euler, and B, it's going to have the regularity C0 in time, H beta minus in space, and L infinity minus in space. That's what it's going to give you. So now, of course, we have to actually construct these things. So now the rest of the proof is going to be active step. Given VQ, RQ with these properties, construct, well, remember that the new stress, I wrote this earlier when I was trying to talk about the cell problem. The new stress is not an arbitrary thing. I mean, the new stress is always going to satisfy this, plus the game is going to be given VQ and RQ. Remember, VQ is also hidden here. Construct WQ plus 1, this budget, such that this new function satisfies this budget. So in fact, now we could actually write, if you want, a minimization problem, because we have a budget and a goal. We could actually write down, find the minimum such that. I just don't know how to do anything with that. And instead, we're going to design this by hand. By hand, based on intuition, we gathered from this analysis of fast, slow variables. What I'm going to do tomorrow.
Time for a quick question.
You mentioned chopping up an H1 function into level sets. Is that related to the convolution error in like other Nash schemes, or is it completely different?
No.
Okay.
So it's simply this. If you want to have a lot of regularity, and we're milking, as you will see tomorrow, this is the most you can possibly milk out of it. You know, this result of MAT is not like a step towards something. It's the end in some sense. So if you want to milk everything out of your thing, you really need to satisfy, you really need to work in the characteristic, or also known as Lagrangian coordinates of VQ. Now, how can you work in Lagrangian coordinates? Lagrangian coordinates satisfy the ODE flow. The ODE flow can only be solved uniquely and in a stable way if you have a Lipschitz vector field. But we just said that we don't have a Lipschitz vector field. We have an H1 vector field. So I can write my H1 vector fields as a sum over every single level set of Lipschitz vector fields. And if I understand the flows of each one separately, maybe I have a hope of understanding what the flow of this H1 vector field does. And so I'm not going to have one set of Lagrangian coordinates. I'm going to have infinitely many sets of Lagrangian coordinates associated to each level set individually. Because if you chop off an L2 function into level sets, you get L infinity functions, right? And that's where this is going. It's not related to anything else. It's really related to convex integration in LP, as opposed to convex integration in L infinity.
The time scale that you wrote there in the L infinity norm, I mean, one of them, you wrote tau q for both, but
thank you, Matt.
It's a bit deceptive.
It's a bit deceptive, I understand. I think this is important enough to address before tomorrow, because otherwise it's a problem. So what I wrote here is correct, but then I shot myself in the foot when I said for L infinity, replace this by 1. You also need to replace this by something in L infinity. It's a different Lipschitz scale, right?
Yeah, and you have a Lipschitz bound. Like to Ben's question, you have a Lipschitz vector field. It's just that the bound is terrible. Yeah,
absolutely right. So in L infinity, these are not the assumptions. This is 1. And this tau q inverse is replaced to really 1 over the Lipschitz norm. So what is 1 over the Lipschitz norm? Well, this in L infinity is 1, and the gradient costs lambda q plus 1. So 1 over the Lipschitz norm is lambda q plus 1. It should be lambda q plus 1 in L infinity, and this should be lambda q plus 1 in L infinity.
Lambda q is the old one.
Ah, it's the old one. Yes. So by the way, back to your question, all these functions are analytic in some sense. So when I say that you have H1 functions, I really mean that your good bounds are only good in H1. All these functions are as smooth as you want. So it's not a question of does the ODE flow exist? It's more about stability. For how much time can I ensure it's close to the data and things like that.
Okay, let's save the rest of the questions for the break and enjoy lunch, and thank Vlad.
Thank you.